Yeah, hello everyone, I'm Haichen Shen. So before I go into our talk, I just introduce a little bit on our program schedules. You already have the schedule program in your hand. So Sandy just gave like an introduction to the scroll. Next, I'm just going to talk about our infrastructure designs and a little bit of our testnet, and I was just trying to do a live demo. And after that, Yingtong from the Dcache, they're going to talk about the programming in the Halo 2, and then some latest progress what happens in the Halo 2. And then Mason is going to talk about our zkEVM architecture and how we construct this zkEVM. And then after the break, I'll come back and talk about some performance optimization we have been done for the zkEVM. Okay, so let me get started. Okay. Yeah. And also, we don't just want to like this be very formal presentation, so you can feel free to ask me, break me, like interrupt me with any questions. I will be very welcome. So okay, so I'm going to talk about our Scroll's architectures. Yeah, just one sentence to summarize what Scroll is building. Scroll is building a EVM equivalent zkRollup solution layer 2 chains to scale the Ethereum and then to bring like allow like more transactions and lower transaction gas cost for the Ethereum. So like we can bootstrap next billion of users. And then before I dive into some technical details and then our architecture designs, I just want to first talk about our design principles that drive the decision of like our design and why we choose this approach we want to build. So there's like 4 principles, and first and foremost, which is the most important things, is what we think, we believe that ensuring the user security should always comes first. And then for Scroll, this means that the layer 2 transaction should have and share the same security level as the transactions that are happening in the Ethereum today, and then without trusting even the layer 2 operators. And then we should, like during the design, we should never trade off any user security for any like efficiency or any other like the reasons for that. So just need to guarantee the user security, like user can always maintain the access to their funds on the layer 2 or layer 1. And then second, we think an effective EVM equivalent solution, an effective Ethereum scaling solution should allow users and developers like a smooth path, like a seamless migration path from the existing dApps and then existing developing tools. And then we believe that maintaining the EVM equivalence is the best way to achieve this goal. And then third, the decentralization is one of the key aspects of the blockchain. Usually it's like the overlooked or improperly traded for some efficiency reasons. But we think like decentralization is one of the key property and that we should maintain even at the layer 2 context. And then so like in the Scroll, and also the decentralization can guarantee a protocol to be very resilient to any censorship or coordinated attacks. So like in the Scroll, we consider the decentralization across many different aspects and then different layers, including the sequencers, the provers, and then the community of users and developers. And then fourth, for a user to enjoy a great user experience on the layer 2, so we believe like there's 2 important things we need to achieve. One is that the transaction fee on the layer 2 should be way cheaper, like orders magnitude cheaper than the base layers. And then the second is that user should experience some instant pre-confirmation on the layer 2s and a reasonably fast finality on the layer 1s. So this both like requires a good efficiency you can achieve in the layer 2s, so that like to be able to have a great user experience. Now next, let's take a look at like how we use these like design principles to guide our decisions in our approaches. So first, ensuring the user security and maintaining the EVM equivalence lead us to a zkEVM based zkRollup solutions. So first, the zkRollup is like the best. It's guaranteed like a very great security by relying on the mass and the zero-knowledge protocols on the behind. And then the zkEVM, which achieves the EVM equivalency, is the holy grail inside the zkRollup solutions. And then you can maintain the EVM equivalence, meaning that all of the user experience and the developing tools will be just directly compatible with the layer 2 when you have the zkEVM. And then zkEVM, because it's a zkRollup solution, so you still have to share the security guarantee from the zkRollups. And then second, the decentralization leads us to design a decentralized approval networks. So when we start designing the zkEVM solutions, we quickly realize that putting the Ethereum virtual machine into the zk proof will lead to resulting a great overhead for generating the proofs. So in order to reduce the time to finality on the layer 2s, we decided so we should build a decentralized prover network that's going to help us to generate the zk proofs. So there are two main benefits for having a decentralized prover networks. So first, the community, like whoever can, we have like if we because we have this seamless, this permissionless decentralized prover network, any community member can come and run a prover node, and then the community will be incentivized to build a better, substantially better solutions, including like both hardware solution or software solution to boost up, to help reduce the proving time so that we can have a better solution for to generate a zk proof. And then second, when we're designing our proving infrastructure, we make sure like it's highly parallelizable, meaning that if we want to scale up, we can very easily scale up by just simply adding more prover nodes into our network, so that I can get like achieve very great throughput for generating the zk proofs. And then third, so for the efficiency, so to improve the efficiency of the layer 2s, so our approach is to leverage all of the innovative research-driven solutions across all of the community. So our zkEVM designs takes advantage of like many recent breakthroughs in the including the zero-knowledge proof systems, and then the proof aggregation, and then the very like innovative hardware acceleration solutions. And then second, so we also focus on like to develop in the open source manner, so that this allows us to collaborate with a lot of open source communities, including the PSE team from the Ethereum Foundation and other open source collaborators and contributors. And then we believe that like all of the community contributed to this like open source approach, so can lead to a best and then most effective and efficient solutions for the zkEVM and the zkRob. Okay, next I'm going to talk about the scroll architectures. So first I was just going to talk about like the basic like modules and components that happens inside the scrolls architecture. So first you have like layer 1 chain, which is the Ethereum, and then the layer 2 is the scroll chains. So in the Ethereum, there are mainly two parts. Like there's two contracts deployed on the layer 1. One is the bridge contract for mainly for bridging any assets or like relaying any messages between the layer 1 and layer 2s. And then actually like this bridge contract will be also, there's one part of bridge contract deployed on the layer 1 and one part will be deployed on the layer 2s. And then the second contract deployed on the layer 1 is the rollup contract, which we're going to accept the data availability transaction that are going to include some block data and the transaction data inside the rollup contract. And also it include a solidity verifier to verify the zk proof that are going to be sent to the Ethereum for the finalized any blocks. And on the layer 2, the main functionality is coming from the scroll node, which is responsible for generating layer 2 blocks, accepting RPC requests, and also like relaying the messages, and also generating the proofs. That will be all like happens in responsibility for the scroll node. So inside the scroll node, there are three modules mainly. The sequencer is basically just processing the layer 2 transactions and generate layer 2 blocks, also processing any RPC requests. So our sequencer implementation takes a fork of the Go Ethereum implementation with some minor tweaks for the layer 2 purpose. And then because like the Go Ethereum is the most popular execution client for the Ethereum node. So like by directly forking based on the Go Ethereum, so that gives us the best compatibility with all of the existing tools, and then all the RPC interfaces will be the same as like when you interact with the Ethereums. And then second, inside the scroll node, there's a relayer which is going to monitor all of the smart contracts we deployed on layer 1. For example, if find any deposit event happens on the bridge contract, is going to relay this deposited message to the layer 2s. And also the relayer will be responsible for submitting any rollup contracts, rollup data to the rollup contract. And then third, there's a coordinator here inside the scroll node. The coordinator is going to watch for any new blocks and getting the execution trace from the Go Ethereum. And then once the coordinator receives a new execution trace for a new block, and they're going to dispatch this execution trace to one of the rollers inside the roller network. And then just ask the roller to to generate the zk proofs. And then the roller, then if it finishes the zk proof generations, it'll just send it back to the coordinator, and the coordinator just will relay that to the relayer for the rollup to roll up the validity proof. And then inside the roller, so we can talk about the roller as well, because the roller is mainly contact with the coordinator. So the roller is basically running a zkEVM inside. And then we also expect the roller to be run on a hardware accelerators in order to reduce the time to generate a zk proof. Because the zkEVM is quite heavy zk circuits and very complicated, so it's somehow if you use the accelerators, you can be reduce the total time to generate the proof. And then right now we are using a GPU prover to generate the proof, but we expect the community and new hardware companies can come up with new accelerators can further reduce this proof generation time. And then all of rollers basically is a prover node. And then we have this decentralized prover network which is run by different community members in the future. Any questions so far? Okay, so we can also take a deep, closer look into what happens inside the roller when you're generating the proof. Because it's also just not very simple just running the zkEVM. So first, the roller will receive this execution trace from the coordinator. And what's inside this execution trace? It includes the following things. First, it has the execution step when you execute transactions inside the Ethereum virtual machines. For example, you will execute all of different opcodes like add, multiply, or push and pop to the stack, and then read or write to the memories, and then including also you're getting any block informations from the block headers. And the second thing, it will include the block header and the transaction data going to be the input to the execution trace. That when you need to get any information from the block header, and also what transaction data, core data you have. And then third, we also need to load all of the contract bytecodes to make sure that we are actually executing the bytecodes actually from the deployed contracts, not from arbitrary opcodes. And then last is there's some Merkle proofs. They're going to prove help you to prove the Merkle tree transition from the old state root to the new state root. And then after you the roller receive this execution trace, it will just hand this execution trace to a module called circuit import builder. This circuit import builder is going to transform all of the trace output from the Go Ethereum and then assign into the certain circuits, and then which will be a 2D giant matrix. Probably you'll get more idea after Yingtong, and then Mason talk more about Halo 2. So I'm just going to have this a few giant two-dimensional matrix, and then you're going to expand all of the execution trace, and then also generate some auxiliary data that helps to generate the proof, and then feed into all of the witness in those circuits. And then next, when we talk about zkEVM, actually it's not a single circuit. It includes a set of circuits that works together to generate the proofs. So because if you have everything inside a single circuit, then it will lead to a even greater overhead. So that's why we separate them into different parts of circuits, and then connect them through some lookup tables, which I think Mason will talk more about that in his talk. So this gives you some flavor of what circuits inside the zkEVM. There's a EVM circuit. It's the main core circuit that proves the transition of this virtual machine state from the previous step into the next state by applying some of the opcodes. And then this RAM circuit was going to constrain any read-write operations happens inside the Ethereum virtual machine, including the stack push and pop, the memory read and write, and then the storage modification. And then the storage circuit is actually another auxiliary circuit that's going to prove the state transition using the Merkle proofs we talk about in the execution trace. Apply those Merkle the proofs for every change, including read and write on top of the inside the storage circuit that can prove the state root is actually transited from the old one to the new ones. And there are also a few other auxiliary circuits I won't just talk about here in this talk. And after you run all of the circuits, so each circuit will actually execute one proof. So there will be a bunch of the proofs you collect from executing the zkEVM. But if you're uploading all of the circuits into the layer 1 and then validate them one by one, then it definitely will be resulting in a very large gas cost in the layer 1. So in order to reduce the gas cost for the inside the layer 1 verification. So we need to further using an aggregation circuit that aggregate all of the proofs from the zkEVM and then into a single aggregation proof. And then here we just call it a block proof, which corresponds to a single block. So the aggregation circuit, what's inside the aggregation circuit is it just replicate the verification logic and then just represent it inside the zk circuit so that it can be redo everything like you need to do inside the verifier, and then you can do that inside the circuit. That would be, and then you'll generate a new proof that's going to, once you verify this block proof, you just basically verify all individual proofs inside the zkEVM circuits. Okay, so this is what happens inside a single rollers. But like usually it takes a longer time to generate a single zkEVM proof for than generating a block. That's why like we will have multiple rollers that's going to run in parallel to generating the block proof for different blocks. And then if you want to further reduce the overhead of the verification on the layer 1s, so you can reuse this aggregating circuit and then to aggregate those block proofs again into a single proof, so that you can only use verify a single aggregation proof that can verify all of the blocks inside in this aggregation proof. Okay, so previously like this, I just described all of the modules inside the zk inside our architecture. Next, I'm just going to show up like how that works in actions when to do inside the zk Rollup. So in the zk Rollup, like the overview is like you have two chains. One is the SBC chain, and one is the layer 2 chains. Here is a scroll. So the layer 2 chains can generate more blocks than the layer 1. So like one layer 1 blocks, maybe you can within that time period, like 15 seconds or 12 seconds after the merge, and then you can generate multiple layer 2 blocks. And then what you're going to do is like you're first going to aggregate all of the blocks within that time or period, and then can just send up all of the data, like the block data or like transaction data, and then roll up like send to the next blocks inside layer 1s. And then like after a while, because the proof generation takes a longer time, then you can have like an aggregation validity proof that aggregates the previous batch of the blocks, and then you can send that proof into even later blocks inside the SIM. And then after that, the block basically can be finalized. So with that, you can actually have the different status of the layer 2 blocks. So first, initially, the block, once like a block is proposed by a sequencer and included in the layer 2 chains, we call it a pre-committed status. So when a block is pre-committed, it's still, so like this block is not a like canonical part of the layer 2 chains because nothing has been settled like or sent to the layer 1s, but you can still do some actions like optimistically on top of the pre-committed blocks based on layer 2s. And then second, so once the block is generated on the layer 2, so you can collect all of the data you need and then just send that posted to the Rollup contracts on the deploy on the SIM. And after that transaction is confirmed, then this block can be transited from the pre-committed status to the committed status. And with that, you have more confidence because the data of your transaction means like it already be written to the layer 1, so no one can modify that again. So it just only seems like it's not sure inside committed status is you're not sure that your transaction has been executed correctly on the layer 2s. So in order to finalize a block, you need to then use the zkEVM to generate a validity proof of all of the layer 2 blocks and all of the transaction like steps that happen. And then you send that validity proof to layer 1 and then be verified by a verified contract. Then that means like this block has been finalized, and then that block has been finalized as a canonical part of the layer 2s. So to like see like more concrete example, like in the context of a scroll. So first, like you have a block generated by the sequencers, and then you will roll up the data from this block and then send up to the Rollup contract. And then after this block has been confirmed, transaction being confirmed, then the block status should be changed from a pre-committed block to a committed block. And then meanwhile, you also will extract this execution trace from this block and then send that to the coordinator and then being forwarded to one of the roller for the proof generation. And then you can do that for every like the new blocks you get. And then you like there are multiple rollers is going to generate the proof for each block. And then after a while, the coordinator will collect a few the block proof from those different rollers together. And then you can further create a special task with all of the block proof and then send to another roller for this aggregation proof generations. And then after that, the proof generation, the aggregate proof generation has been done. You receive this aggregation proof. And then you can roll up, send that proof into the layer 1 roll up contracts. And then that verification contract will take all of previous data, like you roll up to the contract as the public input to this verified contract, so that you can then finalize all of the blocks that are being included inside this aggregation proof. Okay, so I'll probably quickly go through how the bridge works. It's I think running a little bit late, but I think so how does bridge work is it's quite standard for the layer 1 to layer 2 transactions. So the user just interact with the bridge contract inside the layer 1 deployed in Ethereum. So you do call deposit token function inside the bridge contract, and then that bridge contract will just emit one event inside the bridge contract. Say someone just deposited some tokens, and then the layer 1 bridge contract will just freeze this the token, whatever token user transferred to the layer 1 contract, and it'll just freeze inside that contract. And then the relayer will just monitor all of the events generated from the bridge contract, and then wait for a few confirmations on the layer 1s. And then after that, it will just then send a transaction to send a new transaction in the layer 2 bridge contract. And that bridge contract will then either mint a new token for the ERC or just transfer some Ethereum Ether to the user's layer 2 address. And then second, on the other hand, if you want to withdraw any tokens from the layer 2 to the layer 1, you interact with the layer 2 bridge contract called to withdraw the tokens. And then the layer 2 contract, bridge contract basically will also emit an event that relayer we're going to monitor. But at this time, so relayer does no longer wait for layer 2 block confirmations. It will wait for this block that including this withdraw transaction to be finalized in the layer 1. At that time, then it will send out this transaction to the layer 1 bridge contract, which then finally will transfer that token to the user's layer 1 address. Okay, so for our pre-alpha testnet, so we have Scroll layer 1, so we deploy as a fork of the Ethereum with the proof of authority-based consensus, and then Scroll layer 2, which is a zero-knowledge rollup, deploy on top of the Scroll layer 1. And right now we are running 5 provers, a small cluster on the back. And then, so right now as I talked before, we only have the block proof, so we just meaning we just roll up every blocks, generate a proof for every block, and then just roll that block proof to the layer 1. We haven't finished the aggregating multiple block proof into a single proof. And then we have a few pre-deployed applications on top of the pre-alpha testnet. So we have faucet application on top of the Scroll layer 1. And then second, we have a bridge contract on both layer 1 and layer 2 for any relaying for transfer tokens between layer 1 and layer 2. And then a swap application that is a fork of the Uniswap v2 that's going to give users ability to swap tokens and also provide liquidity on the layer 2s. And then we also have developed a small Rollup explorer that's going to show the block status, whether it's being pre-committed, committed, or finalized on the layer 2. So you can see all of the block numbers, and then corresponding block hash, and then whether it's finalized or not. And they're also going to show this transaction hash that's going to, for example, the commit transaction hash will correspond to the transactions that are going to roll up the data, and the finalized transaction is going to correspond to the roll up the validity proof to the layer 1. Okay, so before I go into the demo, so there's also you have you can sign up to become an early testnet contributor. So there's a sign up at scroll.io, so you can still sign up, and then we're going to allow allow a few hundred people to come and test this testnet. And yeah, and then also we're hiring. This a page for hiring page. You can find all of the open positions on our website.